Have you ever stored anything in your attic and had to climb up there in the middle of summer to get it down? Or maybe gone up there to run wire or install insulation? If you have, you know that it's usually not a pleasant experience, and this can become even more dangerous when it gets too hot.
Let's talk about what makes it dangerous and what I would be looking for in this experiment. Since climate change brings more heat waves, this is becoming more and more prevalent. From a NASA climate article, heat index is a measurement of what the air temperature feels like to our bodies, but usually requires calibration and is kind of subjective. Because of this, scientists have started measuring heat stress in terms of something called wet bulb temperature. You may have heard from your dad or uncle or something that it's not the heat that'll get you, it's the humidity. Well, there's some truth to that. To quote the article from NASA, wet bulb temperature is the lowest temperature to which an object can cool down when moisture evaporates from it. The lower the wet bulb temperature, the easier it is for us to cool down. It measures how well our bodies cool down by sweating when it's hot and humid, and tells us if conditions may be harmful to our health, or even deadly. It is theorized that the highest survivable wet bulb temperature is 95 degrees Fahrenheit, which is about 35 degrees Celsius, and only for a very short period of time. High air temperatures and high humidity make for a deadly wet bulb temperature. The scientific reason that this is so dangerous can be explained by Colin Raymond of NASA's Jet Propulsion Laboratory. Once the wet bulb temperature exceeds 35 degrees Celsius, no amount of sweating or other adaptive behavior is enough to lower your body to a safe operating temperature. So if we can't sweat, we can't naturally cool our bodies down, and that's when things really go south.
From the beginning, my goal was to take timed measurements of the attic's temperature and humidity so that I could determine how dangerous and extreme the conditions were. But this evolved into something a bit more complex than that, and my methods changed along the way. But as it got more complex, I would say that I did learn a lot. At first, I wanted to use an Arduino with an SD reader module and a temperature and humidity sensor to measure the conditions of the attic over a week's time, but I ran into many issues with recording usable data. But while working through the issues, the experiment eventually evolved into reading both the outside temperature and the attic temperature so that I could have a point of comparison. There were multiple failures with the original setup, and ultimately the working configuration used both an Arduino and a Raspberry Pi. Alright, so here I have my Arduino Uno that I used, but really any Arduino would do the trick. Here's a Pro Micro, for example. You could use that too. But I also had these sensors, the DHT22 modules. They're rated to read temperature between negative 40 and 80 C and humidity from 0 to 100%. And this is supposed to be with plus or minus 1% accuracy, but I did not really observe that, and that could have been my fault, but more on that later. I also used a lot of Wago lever nuts. These are great for prototyping and electronics hobbyists. If you've never used these before, these are great for making really quick connections. And for the wiring, I used a two-conductor, somewhere like I think 20 gauge solid two-conductor wire that was doorbell wire, I believe, just kind of a spool that was sitting in my basement that I had. So that's what I used. So I had to kind of double it up, 2 runs per each of these since they have 5-volt ground and data lines. And then lastly, connected to the Arduino, I use these little micro SD reader modules that are connected to pins on the Arduino, as seen in the circuit diagram. And with that, let's talk about how I set all of this up.
Here I have a circuit diagram that I made with some software called fritzing. If you haven't heard of it, it's a great way to clearly and neatly show connections for common components, and you can even add your own. I powered the sensors and the SD reader with 5 volts from the Arduino. The sensors communicated to the Arduino through digital pins 7 and 8, but you can use whichever you want. The pins for the SD reader, however, do matter and are connected to 10, 11, 12, and 13 for an Arduino Uno. The Arduino itself received power from an AC wall adapter to the USB port. Once I had these connections set up inside, I started by experimenting with the sensors and made sure that my program could first read the right values. There are libraries that have been written to help with this. After verifying that my code could read both sensor values, I learned how to implement the microSD card reader to log the data. More information on my blog for resources and the code. The link is on my channel page and in the description. When I set it up for real, I had the Arduino placed on a shelf in my garage near an outlet and trailed the wires for the attic up the wall and along the ceiling to reach the attic hatch. I then stuck the sensor up there a few feet from the opening and had to use a small nail through a hole in the housing to keep it in place. For the outdoor sensor, I trailed the wire through a gap next to the back door's frame and shoved this outside to be mounted on the exterior brick mold. I later realized that this was not a prime spot for this, not because of rain or anything, but because of the sun. It definitely was skewing the temperature readings later in the day, since that side of the house faces west. After setting this all up, I ran some short-term tests, and it was promising. I was getting reasonable data based upon the forecasted temperatures and humidity. When I began the first full week test, it was the evening of August 9th, still a prime time for some hot weather. The next few days saw temperatures near 90 degrees. However, when I checked back exactly a week later, I was disappointed to find that my readings had lasted exactly 24 hours and then failed. This was indicated by repeat values for every reading after 24 hours.
I tried a few different things to fix it, but I still had failures before the 24-hour mark. I figured that the 24-hour timing was not the cause of my issues, and I really needed a change of strategy completely. As I mentioned in the project overview, I figured out that I could use a Raspberry Pi and an Arduino in tandem to create an effective data logger. While getting frustrated over the Arduino method, I wondered if my issues had anything to do with the lack of RTC, or a real-time clock module, since most of the Arduino data logger demos online used one. But I didn't have one, and I didn't want to buy one, so I looked into using my Raspberry Pi. I realized that as long as the Raspberry Pi had an internet connection, it didn't need an RTC. It could just keep accurate time when connected to the internet. I found an example of an Arduino communicating to a Raspberry Pi over serial connection, plugged directly into one of the USB ports. I then found an example that used Python to log incoming data to a spreadsheet and made an effort to combine these two examples.
When I started testing it, one of my first problems became how to initialize the Python script if the Raspberry Pi was running without a screen in the garage. I came across a few methods of controlling a Pi in this manner, but the easiest solution was to use RealVNC. This software allows users to access and control the Pi interface from a computer, tablet, or smartphone. Obviously, it's more intuitive to use a computer in most cases, but for the sake of convenience, a phone works great if you're just observing. Once I had this set up, all I had to do was load the Arduino sketch, plug the Pi and Arduino into the outlet in the garage, pull up the RealVNC software on my laptop, and run the Python script. After running the first tests, I eventually ran into issues with the attic sensor. In fact, it was all too familiar. I saw repeated values after a short time. I tried some troubleshooting, but I got frustrated after a while and bought new sensors to replace the attic one. And it worked! After sorting through all of that, I was finally able to run a successful full week test. By this time it was September, and a lot of the super hot weather had gone for the season. When I sat down to look at my findings, the data logger had amassed over 10,000 data points over a week's time. This was initially very intimidating, but Excel was on my side. I wanted to find a source to compare my outdoor readings to, and stumbled upon a site that recorded hourly data from my city's airport. I manually entered these figures into my spreadsheet and used the sort and filtering features to isolate and compare these figures with my own. Some notable results from this are the average errors between temperature and humidity, mine versus the airport's readings. The average difference between temperatures was 6.6 degrees Fahrenheit, and the average percent error between temperatures was almost 10%. The average difference between humidity was 9.6%, and the average percent error between humidity was almost 15. Also, when looking at all of the readings, I found the highest figures for the attic and outdoor temperature and humidity. The highest outdoor temperature was 101.66 degrees Fahrenheit, and the highest outdoor humidity was 85.7%. The highest attic temperature was 123.62 Fahrenheit, while the highest attic humidity was 68.2%. But perhaps the discrepancies should be taken with a grain of salt, for a couple reasons. Firstly, the location of the outdoor sensor was not ideal, since it was getting the full force of the sun in the afternoon and evening. This was clearly causing a huge discrepancy for this time of day. Also, maybe a little bit less likely, but the readings could be mismatched due to the geographical location as well, since my house is miles away from the airport. Not to mention they probably have expensive, higher-grade equipment to take these readings. Overall, I think it was an interesting way to put my results into perspective. Remember, my original intent for this project was to find out how dangerous the conditions of my attic can be on a hot day. With the amount of issues I ran into over the course of this experiment, I missed a lot of the prime time for recording dangerous conditions. The final full week's worth of data was taken from the 9th to the 16th of September, which didn't exactly break any records as far as outside temperatures go. Regardless, let's see what these numbers mean. Remember this quote from the beginning of the video. Once the wet bulb temperature reaches 35 degrees Celsius or 95 degrees Fahrenheit, no amount of sweating or other adaptive behavior is enough to lower your body to a safe operating temperature. So, where does my attic stand on this scale? From the National Weather Service's site, we can determine wet bulb temperature from relative humidity. The calculator asks for barometric pressure in addition to the air temperature and relative humidity. I looked it up and found that the pressure here is usually around 30 inches of mercury. So, the calculator found that 123.62 Fahrenheit at 19.8% humidity equates to a wet bulb temperature of 84.67 degrees Fahrenheit. This is not really that close to the 95 discussed in the article, but it's still very uncomfortable. I don't really know how long this could be sustained, since this would vary for different ages and other factors as well. But wait! I remembered that I saw some higher numbers while testing one of the old logging setups, somewhere in the neighborhood of 133 Fahrenheit at 30% humidity. Okay, so what if this was the case? Yikes, this would mean a wet bulb temperature of close to 99 Fahrenheit. That sounds miserable, and definitely within the realm of deadly conditions. Maybe in the future I can run a new test when the temperatures are forecasted for much higher, now that I know how to properly obtain the data. That way I could be more certain and see how long these conditions last during the day.
Using the Raspberry Pi and Arduino method seemed to work pretty well once I figured out how to use them in tandem. It seemed that it was a reliable way of saving the data from the sensors, and if I wanted to, I could monitor it in real time. If I'm going to do this in the future, I would probably use the same collection setup, but I would want to change how I read the outdoor temperature. Since it was getting the full force of the sun in the afternoon, I could try moving it on the north side of the house to avoid that. And if I do this in the future, I will keep that in mind first and foremost. Thank you so much for watching this video, and hopefully I will have some nice exciting projects coming up in the future.